All right, welcome to 10.5, area and arc length in polar coordinates. So we're going to look at area, all right, and we're going to find the area of some polar coordinates. So here we go. If f is continuous and non-negative on the interval alpha to beta, where beta minus alpha is between 0 and 2 pi, inclusive with 2 pi, the area of the region bounded by the graph where r equals a function in terms of theta between the radial lines alpha and beta is given by this formula right here. 1/2 the integral from alpha to beta of that function squared d theta. Okay, or we can think about it as, if f of theta is squared, that's really r squared. Okay, so we're really talking about sectors, okay, the area of a sector, and we're adding up all of these sectors. So remind yourself that the area of a sector is 1/2 r squared times theta, okay? So that's the area of one little piece. So what we're doing is we're looking at the sum of all of these changes in that theta, that angle, and we're adding all of those up. And what happens is this piece, these changes in theta get so small that that's where that integral comes from. So it's 1/2 the integral of r squared d theta, and then we can kind of zoom in, and that's where r is in terms of a function, r is a function in terms of theta. So we're looking at 1/2 the integral from alpha to beta of that f of theta squared d theta. All right, so let's just jump straight into our first example here. All right, so we want to find the area of the shaded region. Now in your notes, I don't think this portion is shaded, so we're looking at the shaded region being these two pieces here that's highlighted in yellow. All right, so that's what we're looking at. All right, now we're gonna first, when we start and we try to figure out what the area is, we know the formula, but the key is understanding or finding what that starting angle is, alpha, and what the ending angle is, that beta. Okay, so the first thing we do is we check the table for our starting values and our ending values. Okay, now I'm going to kind of zoom in on the graph again, and you kind of think about it in this sense. Well, all right, if I start here, right, that's when our angle theta is 0. And what we're looking for is when we plug it into our function r, this guy right here, 2 minus 2 cosine theta, well, we better get 0, right? Because that's our starting point there. So that's kind of how we test some things. And then as we keep going, it looks like when theta is pi over 2, right, what's our r value there? So that's kind of how we check and test to make sure that those values actually match the graph that's given to us. Okay, so if I start with theta being 0, when I plug it into our function 2 minus 2 cosine theta, do we get 0? Well, cosine of 0 is 1, 2 minus 2 is going to be 0, so that works out, that checks out. So that means we can say alpha is this point here, so we're starting at 0. All right, now remember it looked like we ended at pi over 2. So when we start at pi over 2, when we plug that into our theta, do we get 2? Because on our graph, the radius ended at 2. All right, so cosine of pi over 2 is 0, so then we are in fact left with 2, so that checks out. So that means our alpha is 0 and our beta is pi over 2, so we can go ahead and set up our integral. Okay, now if we're looking at our graph, we can just find the area of one of these pieces, and then all we would have to do is double it. Okay, so let's go ahead and talk about the area of one of those shaded regions, and then we'll continue on with the rest. So using that formula, 1/2 r squared of the integral of r squared, okay, our alpha is 0, our beta is pi over 2, r is 2 minus 2 cosine theta, and we're squaring that. Okay, so now if we want the total area, we just have to double this entire integral. So it's really 2 times that quantity. At the same time, I squared this binomial, and we get 4 minus cosine theta plus 4 minus 8 cosine theta plus 4 cosine squared. Using a trig identity, we can go ahead and say cosine squared is 1 plus cosine 2 theta over 2. We can integrate these pieces. The 2 times 1/2, those guys cancel. All right, so we are left with integrating 4, we're at 4 theta, evaluating that from 0 to 2 pi. Negative 8 cosine theta, we get negative 8 sine theta evaluated from 0 to pi over 2, and we're still integrating this guy here. Okay, so cleaning this up, it's really the integral of 4 divided by 2 is 2 times 1, integrating, 2 times 1 is 2, so we get 2 theta, and we'll integrate that, or evaluate from 0 to pi over 2. And then we're just left with 2 times the integral of cosine 2 theta. Doing a quick U substitution, we could integrate that piece here, and then we'll evaluate everything, gather our like terms, and we end up with the area, the total area of that shaded region being 3 pi minus 8. All right, let's take a look at our next example here. We want to find the area of the entire region, but so all of this, okay? But what I'm going to do is I'm going to focus on just this highlighted piece and call that area 1. And then what are we going to have to do? We're going to have to multiply this area by 4 because there's 4 pieces here, right? So we've got this piece, then we've got this piece, and then we have this piece to add together, okay? So our first goal is to figure out what alpha and what beta is. Now, keep in mind, this time we're given what r squared is already, okay? So it looks like when theta is 0, right, r squared, well, we could say r is just past 2. Okay, so let's just see if that holds true. So we're going to plug into our table of values, right? And we know r squared is really equal to 6 cosine of 2 theta. So when we plug 0 in for theta, we get r squared to be 6. So that means r is just over 2. It's between 2 and 3. So that checks out according to our graph. Okay, so now as we continue on, as our graph continues on, I'm thinking, well, maybe alpha is pi over 2, right, where we end. So we kind of have to see what's going on here. So we can test pi over 2, okay? Does pi over 2 get us back to 0? Because at that point, we're at 0. So when we plug pi over 2 in, right, cosine of pi over 2, or 2 times pi over 2 is going to be cosine of pi. Cosine of pi is -1 times 6. That gives us -6. Well, that doesn't work, right? That is out of that domain. It should be 0. So I have to just eliminate this guy. I can't even use that guy. So what is it, right? So as we look at the graph again, we can say, oh, well, if we look at this line here, it looks like the graph is approaching that pi over 4. So this right here is pi over 4. So as we're continuing on, as theta is getting bigger, right, what are we approaching? Well, it looks like we're approaching the angle pi over 4. So let's just try that in our table. So if we do plug pi over 4 in, do we get r squared to be 0? Okay, so we check the table. When we plug pi over 4 into theta, we get cosine of pi over 2, which is 0, times 6. We get 0, so it checks out. So that means we're able to identify that our theta is 0, or sorry, our alpha is 0, and our beta is pi over 4. So now we can go ahead and set up our area integral. So the area of one piece is 1/2 the integral from 0 to pi over 4 of r squared d theta. Now remember, r squared is already given to us, so it's just that substitution. So then the total area is going to be this area times 4. right? So as we clean up that integral and eventually evaluate that, you can see that we end up with the total area of being 6. This next example is a little bit more complex, so if you do have questions, make sure you ask in class. All right, so now we're going to find the area between the inner and outer loops for this function r equals 3 minus 6 sine of theta. So that's this guy here. So what are we really trying to find? We're trying to find this area, okay, between the inner and the outer. All right, so that's our goal. So how are we going to do that? Well, again, we need to figure out our alpha and our beta. Okay, so the first thing that will kind of help us figure out these key pieces in this graph, right? We can see we've got this piece here, and it hits 0 here. This is kind of an important piece that we're going to call C. We loop back around to D, and we'll continue on this trend, okay? Now, let's find out what those pieces actually are, though. So just like before, let's go ahead and actually graph this on our sine function. Okay, so r is equal to 3 minus 6 sine of theta. We can rewrite this negative 6 sine theta plus 3. So that just means we're going to go up 3, and that's kind of like our 0 marker there. Since it's negative, that means we're going to start by going down, all right, and then continue this trend. So this is just one period is 2 pi. All right, so we can kind of go ahead and draw that graph. So what are some key pieces here? Well, this is where we started at, let me zoom out so we can kind of see the graphs, both graphs together. So we start at A, right, and that's when our radius is 3. As we're going around, we loop. When our radius is 0, that's our B. At pi over 2, our radius, notice our radius is going to be negative, all right? So at pi over 2, our radius is going to be negative 3, all right, which makes sense. So this is point C. We continue on. So then at our point D, which we'll figure out what that angle is, all right, we're back to our radius of 0. And then at part E, we've got a radius of 3 again. And then going all the way to 3 pi over 2, our radius is 9, which makes sense with this point F, okay? And then we loop back around at 2 pi. We're back to that starting point, okay? So these are kind of all the important pieces that I've got highlighted here, all right? And let's just see where that takes us. Now, kind of going back over here, that B and D portion, that's pretty important to our area. So we need to figure out what those angles actually are. So we know the radius is equal to 0, so we're just setting that function equal to 0. That means sine of theta has to be 1/2, which means theta has to be pi over 6 at point B and 5 pi over 6 at point D. So now we're just going to plug this all into our table, all right, for theta comma r, and we're going to see what we've got, okay? So we know at theta equaling 0, our radius is 3. That matches our graph here. At pi over 6, we do get our radius to be 0. At pi over 2, our radius is 3, but it's negative. Okay, so we're at pi over 2, but because it's down here, we know that the radius has to be negative. Okay, at 5 pi over 6, we're back to 0. All right, at pi, we're at 3, so that's our point E. At 3 pi over 2, we're at 9, and then we continue on at 2 pi, we're back to 3. Okay, all right, so what are we looking at here? Well, if we kind of loop around, from B to C, that portion is the inner portion, half of the inner portion, right? That's this guy, oops, that's this guy right here. Okay, and then if we continue looking from D, so back here, all the way to F, that's half of the outer portion, right? And so if we can find that area, that green area, all right, we'll be able to double that to find the total area, okay? So if we kind of look again at that, from B to C is half of our inner, and from D to F is half of the outer, okay? So the area between, so this green area is what we're trying to find, is going to be 2 times half of the outer minus half of the inner. So we're going for the outer from D to F, and the inner is going from B to C. So that's going to help us figure out our alphas and our betas, okay? So now we can go ahead and set up our area formula, right? So 2 times 1/2 of the outer, right? So this is the outer portion, half of the outer portion, from 5 pi over 6 to 3 pi over 2. And then we're going to subtract half of the inner portion. So this is our inner portion. All right. And inner goes from pi over 6 to pi over 2 of our r squared. Okay. Now, 2 times these 1/2, those are going to cancel. And so that just gets us our cleaned up integral here. Now, I'm going to do a quick side note of squaring the 3 minus 6 sine theta. So we're going to jump over here to the green, squaring that, all right, and also noting I'm going to use that trig identity for sine squared. So sine squared is 1 minus cosine 2 theta over 2. And now just cleaning this up, so 36 over 2 is going to be 18 times 1, and then minus 18 times cosine of 2 theta. Now we're going to have to integrate both of these. So I'm just still doing the side note, integrating these guys, right? So 9 plus 18 is 27, so integrating that we'll get 27 theta. Integrating negative 36 sine theta, we get 36 cosine theta. And then integrating cosine of 2 theta, that's our u substitution, all right? And we'll get negative 18 times 1/2 sine of 2 theta. All right, so I just plugged that in over here to kind of save us a little bit of time. And now we're just evaluating both of those pieces from our alpha to betas, right? So as we do that and we just plug in, you can kind of work through this on your own. And what you should eventually get is 9 pi plus 27 root 3. Again, if you have any questions, make sure you ask in class and we can go through it.